and screen. This is the separation between object and screen. Between object and screen. Between object and screen. And screen. And this focal length is important. F is the focal length of the lens. So displacement, through displacement method, you can relate this x, the focal length of the lens, and this distance t. Just note it down. Just you can, if you want, you can draw the ray diagram. You can draw this diagram. Then I will just show you the direct relation that we'll be using in numericals. Written? Can I scroll it now?
1 minute, sir.
1 minute.
Tell me once you have written. I'll change the slide. Written?
Yes.
Okay. So now I have to go through the definition. Yes. This is the final result that you use in numericals. So the focal length is d square minus x square by 4d. This is the relation between the focal length, the x, which is the separation between the two positions of the lens, and capital D, which is the separation between the object and the screen. Please note it down. And this is the question given in NCRT, which is based on this method. Just note down this formula and then this question.
So what is x in the formula?
X is the separation between the two positions of the lens. I have mentioned X in the diagram also. Separation between the two positions, L1 and L2 of the lens.
Sir, we don't need to do the derivation for this.
No, it's not a part of the syllabus. Note down the question. Okay, so let's solve this question together. So what is 90 centimeter here in this formula? This question is based on this formula only. What is 90 centimeter in this formula?
Capital D.
Yeah, this 90 centimeter is capital D. And this 20 centimeter, this is X. This is the separation between two locations of the lens, two different locations of the lens. So that's X. So the formula based thing, D is given, X is given. You can just put the value of D and X here and get the formula, the focal length, which is 21.4 centimeter. Write it down. Once you know this formula, this displacement method, you can directly calculate the focal. Okay, after this question, the last topic of ray optics, there is one topic which is a combination of lenses. Although that topic is not a part of syllabus, like it's been deleted a few years ago, but we will do that topic. There are some questions which can be asked from that topic, so I don't want to leave that topic. But we'll not do the derivation, we'll do just the relation and the numericals. An important topic, you should know that thing. Yes, everyone have written up to here? Arpit, Anshika. Yes, if you have written, can I scroll it now?
Yes, sir.
Okay, so the next is the combination of lens. So combination of lens is that's combination of lens. So if you have two lenses, these two lenses can be two convex lenses, or it can be two concave lenses. It can be a combination of a convex and a concave lens. If you have two lenses which are placed in contact, then what you can do, see, these two lenses are placed in contact. There is no separation between these two lenses. So what you can do is you can remove these two lenses and you can use a single lens. Like you can remove this f1 and f2, and instead of f1 and f2, you can use a single lens. That single lens is known as equivalent lens. So when you remove this f1 and f2, you get a single lens, equivalent lens. If you want to calculate the focal length of that equivalent lens, then the focal length of that equivalent lens is this: 1 by f1 plus 1 by f2 plus 1 by f1. Keep on adding all lenses. But while adding these lenses, keep their signs. If your lens is convex, then take that with a positive sign. But if your lens is a concave lens, then take that lens with a negative sign. If the focal length of the combination comes out to be positive, that means your equivalent lens is a converging lens. If equivalent focal length comes out to be negative, that means your equivalent length is a diverging lens. Now, just like focal length, you can also calculate power. What's the relation between power and focal length, Nabil? Relation between power of lens and its focal length?
Power is the inverse of focal length.
Power is the inverse of focal length. So this 1 by f is power of the lens. You can write that power of the lens, equivalent power, is P1 plus P2 plus Pn. Similarly, you can write that equivalent magnification is the product of magnification of individual lenses. So this is how we do. But remember, when we use these relations for combination of lens, this means you can use these relations only if your lenses are placed back to back. There is no separation between the lenses. If there is a separation between lens, then we can't use these relations. So just give me 1 minute. I'm using the wrong slides. Just 1 second. This is it. So if you have different lenses, you can combine them using this relation 1 by f1 plus 1 by f2, 1 by f3 plus 1 by n4. You get the focal length of the equivalent lens. For power, you can just add them up. And for magnification, you can just multiply the magnification of individual lenses. Note it down, please. We'll do one question on this concept and then lens is over. We'll come to optical instrument next. Note down this question, please. Solve this numerical and write your answer in chat room. When you take focal length, keep focal length with proper sign. For a convex lens, the sign of the focal length is positive. For a concave lens, sign is negative. So solve this numerical and write your answer in chat room. Yes, Akshay.
Done.
Answers. See the formula based thing. You have f1, f2. You just have to calculate the equivalent focal length.
सर कन्वेक्स लेंस की फोकल लेंथ नेगेटिव नहीं होती?
कॉन्वेक्स की पॉजिटिव होती है, कॉन्केव की नेगेटिव. मिरर में उल्टा होता है. Okay. Noah is correct. Answers. What about the rest? Nabil, Saifullah, Sakina,
1 minute, sir.
It's a formula based thing. I'm the co-host. Send to co-host, please. Yes. Correct answer, Nabil. No, Anshika. Anshika, you can't add them up directly. You take inverse of them, then you will add. Sefula, correct. Akshay, correct. Miraj, your answer. Yes, Akshay is correct. Yes, Nabil, power is correct also. Akshay is wrong answer. Power, okay, fine. But Akshay, for power, convert your focal length in meter. You can calculate power only if your focal length is in meter. Nazia, it's correct. But for power, keep your focal length in meter. Sakia, focal length is correct, but for power, just convert this in meter. See, the calculation is straightforward. 1 by f equivalent is 1 by f1 plus 1 by f2. So it's 1 by 10 minus 1 by 5. It's minus 1 by 10. So the equivalent focal length is minus 10 centimeter. If you want to calculate power, then keep your focal length in meter. So to convert this in meter, divided by 10. So it's 1 by 10 minus 1 by 10 meter. Now you can calculate power, which is 1 by f equivalent, which is minus 10 diopter. The side root of power is diopter. So remember, to calculate power, your focal length should be in meter. Then you will get your power in diopter. If your focal length is in meter, then only your power will be in diopter. No. So that was about refraction and that was about lens. Next, we're going to start optical instruments. See, the major numericals that comes from ray optics are from lens only, or this refraction only. These optical instruments, and then you have dispersion. It's usually you get derivations from these topics. So optical instruments. So we have three optical instruments. One is eye, another is microscope, another is telescope. So eye is not a part of syllabus for last 5-6 years. Microscope, you have two types of microscope. One is simple microscope, another is compound microscope. Both the types of microscopes are in syllabus. In telescope, you have two types of telescopes, refracting and the reflecting type telescope. But to study microscope or telescope, you should know some basic things about eye. The first thing is the eye lens. This eye lens is basically a convex lens. This eye lens is a convex lens. And the focal length of this convex lens is variable. Like this eye lens can change its focal length. If you want to look at an object which is a very distant object, a very far away distance, then for that particular object, the focal length of eye lens increases. But if you want to look at an object which is very close to your eye, then for this particular object, the focal length of the eye lens will decrease. So eye lens is a convex lens, but its focal length can vary. And then you have retina, which is screen. So you should know this thing that eye lens is a convex lens with a variable focal length. And then there are 2 points. One is near point and another is the far point. Near point is the closest distance from the eye at which you can view an object. So from the eye, if I place an object at 25 centimeter, then you can view it clearly. But if I place this object at a distance less than 25 centimeter, then I can't view this object clearly. So for a normal eye, least distance is 25 centimeter, 25 centimeter from the eye. If you place an object at a distance less than 25 centimeter, then you can't view that object properly. That's a near point. In calculations, we represent near point with minus d. Sorry, with d, small d usually. So we'll be using small d for near point always. For a normal eye, far point is infinity. Means if rays are coming from infinity, then also you can view that object. So for eye, this much you should know that the eye lens is a convex lens with a variable focal length. Image is obtained on screen. The near point for a normal eye is represented by D and it's 25 centimeters, and the far point is infinite. Please note it down. Then we'll start with the very first instrument, which is simple microscope.
सर 1 minute की scroll up.
See the chapters which are left now, like dual nature, atom, nuclei, semiconductors. Each chapter will take one class only. Only this atom can take 1.5 class. Otherwise, each chapter will take just one class. So once this ray optics is over, we'll finish the syllabus very fast. In 1 week or 2 weeks, we'll finish this. So my target is my target was 3rd week of December. So I believe if I take some extra classes, I can finish it by the 3rd week. Or extreme, it will take 1 more week, 4th. That's it.
Done, sir.
So written up to here, can we start with microscope?
Yes, sir.
What is magnification, Anshika? We have discussed magnification in the last class. What is magnification? Anshika, I can't hear you. You're not audible. Arpit, what is magnification?
So magnification for
What is magnification exactly, Arpit?
sir ratio of height of
Sir, it is
image
the
to
height
It's the
of the
ratio of height
with
of
respect
image
to
and height
object.
of object. That's magnification. But when we okay, Anshika, no issues. You can type here. So magnification is the ratio of height of image and height of object. But when we study any optical instruments, it could be a microscope or a telescope, then we don't use or we don't calculate magnification. What we calculate is angular magnification. So what is angular magnification? It's not the ratio of height of image and height of object. Rather, it's the ratio of angle subtended by image and object on the eye. This is how we calculate magnification. I'm repeating again. We will be doing angular magnification in optical instruments. And angular magnification is just the ratio of angle subtended by image and angle subtended by object on the eye. It's the ratio of angle, not the ratio of heights. So angular magnification is the ratio of angle subtended by image and object on the eye. So this is eye, the ratio of angle subtended by image. So this is some image A prime, B prime. This image is subtending some angle beta on the eye. This is our object AB. This is the angle alpha subtended on the eye by the object. The ratio of beta and alpha is known as angular magnification. So we are writing I here, but practically when we will calculate it, we will measure these angles from lens. In every calculation, we'll write I, but we will measure it from the lens. The reason is when you use a telescope or a microscope, your lens is very, very close to your eye. So you take angle from eye or lens is the same. So it's just the ratio of angle, not the ratio of height that we are interested in now. Just note it down. This is how we'll calculate angular magnification every time. So in all instruments, we'll be calculating angular magnification, not the linear magnification. We are not going to calculate ratio of height of image and height of object. We are going to calculate the ratio of angle subtended by image and object on the eye. Just note it down. Then we'll start the instrument. Tell me once you have written, scroll it. Saifullah, Sakina, can I scroll it now?
No one
Yes,
is.
sir.
Tell me once you have written and start this micro.
Yes, sir, done.
So the first instrument is simple microscope. So simple microscope is just a convex lens. It's a convex lens which have a very small focal length and a small aperture. Aperture means size of the lens. So simple microscope is just a convex lens having small short focal length. So we can calculate the magnification in two cases. The first case, your final image is obtained at the least distance of distinct vision, which is 25 centimeter. And in the second case, your final image is at infinity. So you can have two cases. One is when your final image is at least distance, and the another is when your final image is at infinity. So see how we compare these two. First, we take, let's assume that my specs are, there will be two positions of objects here. So let's first understand what does it mean. See, consider this as a simple microscope. This is my simple microscope. So what I will do is I will first remove the simple microscope. I'll take this object. I place this object at 25 centimeter from my eye and will calculate the angle subtended by the object on my eye. So this is the angle subtended by the object, not by the image. Then I put the simple microscope, glasses. Then again, I place my objects in a way so that the image of this object is obtained at 25 centimeter from the eye. Now the image is 25 centimeter. Now I will measure the angle subtended by the image on the eye. Then I will take the ratio of both the angles. I'm repeating again. Earlier, when I was saying the angle subtended by object, then there was no lens. There's no simple microscope, just naked eye. So I take the object, place this object at 25 centimeter and measure the angle subtended by object on the eye. Then I put the lens and then I measure the angle subtended by the image on the eye. But the condition is your image should be at 25 centimeter from the eye. When you take both the angles, take the ratio of both the angles, and that ratio is angular magnification. So it's the ratio of angles subtended by image and object on the eye, and both are at least distance of distinct vision. This is the ratio. Now the ray diagram is important. So I don't want to draw the ray diagram again, so we'll do it in the way. So this is, or I should draw it. Let's draw this ray diagram. See, if you can understand this a simple microscope, then all other instruments like compound microscope, your telescope will be very easy to understand. All instruments work in the same way. Same calculation, same type of results. So you have 5-6 derivations in optical instruments, but all derivations are almost the same. So this is your convex lens, or you can say this is your simple microscope. This is your simple microscope. This is your optical center. This is your object AB. We place this object AB beyond the focus. So the two rays will come. One is parallel to principal axis. After refraction, this ray will pass through the focus. This is focus F. After refraction, the ray will pass through the focus. Then there is another ray. This ray will pass through the optical center. And the point where these two rays will meet will be your image. But see here, if I place this object beyond the focus, then these two rays will meet. You will get an image, but that image will be smaller than the object. If you want a magnified image, then what you will do is, you will put your object in between the focus and the optical center. This will be the position of your image. If you want an enlarged image, then you will place your object in between the optical center and focus. Now what will happen is one ray will pass through the optical center. It will go straight without any deviation. This will go straight. Then you take another ray, which is parallel to principal axis. After refraction, it will pass through the focus. Now see, these two rays are diverging rays. They will not meet anywhere, so you will not get a real image. But when you produce these rays in the backward direction, when you produce these rays in the backward direction, they will appear to meet at a point. So they appear to meet somewhere here. So this is your image, your final image, which is A prime, B prime. And this is the object. This separation between the object and the optical center is the object distance. This separation between the optical center and the image is the image distance, which is equal to D. This is our condition. We'll set our object in a way that image is formed at the least distance of distinct vision at D distance. So this is your image, the angle subtended by image, and this is I. Let's make I here. This is your I. So we'll take angle from, we will write that we are taking angles from the eye, but we will measure angles from the lens always. So we'll write we are taking angle with respect to eye, but practically we are measuring that angle from the lens. So this is the angle which is subtended by the image, and we call this angle as beta. And when your image is at a distance D, D means 25 centimeter. Now you need the angle subtended by object also. When object is placed in 25 centimeter. When we say object, that doesn't mean this object. We're not talking about this object. This is the object when you are using the lens. When we say object, that means without the lens. So that is this object, this AB. This is I. We place an object at 25 centimeter D distance from the eye and we measure the angle. This angle is alpha. So magnification is the ratio of this angle beta, which is angle subtended by image. And this angle alpha is the angle subtended by object on the eye. I'm repeating again, when we calculate alpha, we remove the lens. Alpha is object and I, that's it. But when we take beta, then we use the lens and we take the angle subtended by image on the lens. Is this ray diagram clear for everyone?
Yes, sir.
Ishika, Unib?
Yes, sir.
Because if this ray diagram is clear, if this simple microscope is clear, then compound microscope, telescope, you will see this just the repetition, nothing else. Okay, then please note it down. First draw the ray diagram, then we'll start the calculations. Calculations are straightforward.
Sir, for simple microscopes, then we need two ray diagrams.
Yes, yes, yes. You need to draw a ray diagram.
So we need two, one with lens, without lens, or both can be put in one.
Sorry, can you repeat again?
So we need two ray diagrams, one for with lens and without lens, or we can put both in one.
Usually what authors do, they draw both with lens and without the lens on the same axis. But just for the sake of clarity, I'm drawing differently. Maybe in the compound microscope, I'll start drawing both the object with the lens and object without lens on the same axis. But at least for simple microscope, let's draw it separately. I believe, is this what you are asking? No?
Yes, sir. Yes, sir.
For magnification, you always place your object in between the optical center and the focus. Can I scroll it now if you have written? Nabil, Saifullah, Miraj.
One minute. Done, sir.
Sure.
Done, sir.
Fine. So the next is object distance is u, image distance is d. Draw this one also. Huh? This is your object without the lens. So magnification is basically the ratio of this angle alpha and this angle beta. Let's start the calculations now. We'll start calculation by simple the ratio of beta and alpha. Your angular magnification is the ratio at beta alpha. So let's calculate beta using this triangle ABO. What is tan beta in triangle ABO, Arpit? Arpit, what is tan beta in triangle ABO? Tan beta here?
Sir, in which triangle?
ABO. ABO. What is tan beta here?
Sir, AB upon BO.
Tan beta is the ratio of AB and BO. So this is tan beta. For a small angle approximation, you can write that tan beta is almost equal to beta. In this triangle A1, B1, O, what is tan alpha only? A1, B1, O, what is tan alpha here?
Sir, height of object upon D.
And what is height of object? A1, B1, huh?
Yes.
So A1, B1 divided by OB1. So let's A1, B1 by OB1. So this is beta by alpha m. I'm substituting this equation 2 and equation 3 in 1. So we get m is AB by OB, A1, B1 by OB1. Now both AB and OB1. What is AB here? It's image or object? This AB is the object, height of the object. What is A1, B1? It's again the object. So you can, AB and A1, B1 are the same thing. So when you take ratio, they get cancelled out. See, this AB will get cancelled out with this A1, B1. You are left with OB1 by OB1. And what is OB1? Let's check here. What is OB1? OB1 is minus D. So instead of OB1, you can write minus D. What is OB here, Sakina? OB. In this ray diagram, what is OB here?
Minus U, sir.
Minus U. So you can write OB is minus U. So when you put the value of OB1 and OB here, OB1 is minus D, OB is minus U. So minus minus gets cancelled out. So magnification is D by U. So this is angular magnification D by U now. Next, what you can do is you can just, you have to solve this D by U. Huh? So let's use lens formula. There is one issue with this formula. The issue is with this U. There should not be U. U is something variable. Instead of U, we will try to replace it by F. So we will be using lens formula here. So if I apply lens formula here in this ray diagram here, so object distance will be negative. So you can write U is minus U. Your image distance is also negative. See, image distance is D. So image distance is minus D. It's a convex lens, so the focal length is positive. When you do the substitution, it's 1 by minus d plus 1 by u is 1 by f. So you can say that your 1 by u is 1 by f plus 1 by d. So that is equation number 5. Next, what we can do is we can just substitute 5 in 4. So when you substitute 5 in 4, when you put equation number 5 in equation number 4, what you get is you get m is d 1 by u. 1 by u means it's 1 by f plus 1 by d. So when you multiply with d here, your m will become, your m is, it's d by f plus d by d. And what is d by d? It's 1. So you can say that your m is, it's d by f plus 1. So this is the magnification of a simple microscope when your final image is at least distance. So d by f plus 1, d is least distance. And one more thing, this is not a general formula. It's not valid for every instrument. This is valid for simple microscope only. Even for simple microscope, this is valid for the case when your final image is at least distance. So it's not a general formula, it's a particular formula. So when you use this formula in numerical, no need to consider sign. No need to consider sign. So when you will use this formula in numericals, you will not use sign convention. No need to consider sign. So we don't take D to be negative now. We'll take D to be 25 only. Focal length will be, if given is 5, then we'll take 5 only. We will not use sign convention in any of the formula of optical instrument. We'll be using everything directly. Note it down. Then we'll do the next part.
फिर वो ऊपर वाले पार्ट में लिखो। सर लिख
Sir, what does small d mean?
What is small d?
Small d.
Yeah, that's least distance of distinct vision, 25 centimeter for a normal. The condition is you need final image at least distance. So your image distance is equal to d. Read the definitions very properly. The definition of magnifying power. Ratio of angles obtained by image and object on the eye when both are at least distance. See, if you know this derivation, then you know the derivation of compound microscope. You just have to repeat this thing with two lenses. Everything else is more or less same. Can I scroll it now? Yes, Akshay. Can I scroll it?
Yes, sir.
Okay. So that was about the magnification when your final image is at least distance. Now there is another case. So there is one more thing. So your magnification is positive. That means your image is erect with respect to object. No need to consider sign. And f and magnification are inversely proportional. So we'll use and that's why we use a convex lens with a shorter focal length. So these are the conceptual questions from this topic. This one and this one. Just note it down, please. No need to write this formula, already written this formula. Just write down these 2 points that image is erect and the focal length and the magnifying power are inversely proportional. So that's why we use lens having smaller focal length. So you must have written up. The second is when your final image is at infinity.
So just a minute, the last 2 points. Done, sir.
Okay. So Cephala, for what position of object the final image is at infinity? So at what position should I place my object in front of the lens so that my final image is at infinity? Noha?
At far
Yes.
point, sir.
At?
Far point.
No. I need my image at far point infinity. I'm asking about the object position. Where should I place my object to get my image at infinity?
At
Yashika?
focus.
Yeah, at focus. So when you place your object at focus, then your final image will be at infinity. So let's see if you can explain this diagram. So this is the lens, this is the convex lens. You place an object at a distance f from the convex lens. F is the focal distance f from the convex lens. So there is one ray which is parallel to principal axis. After refraction through the lens, it will pass through focus. So this is the first ray which is passing through the focus. Another ray is passing through the optical center. So when you produce them in the backward direction, they appear to meet at infinity. So the final image is at infinity. So the only difference between this case and the previous case is, in the previous case, your object was in between focus and optical center. But here your object is at the focus. So these are the rays which are going to infinity. These rays are going to your image. This is image. So the angle subtended by image at the lens is beta. And your object distance is equal to it. Now, you remove the lens and you place your object at a distance d. So this A1, B1 is your object with the naked eye. So in the previous case, I draw these two things separately, so that there is no confusion. From now onwards, I'm following all authors. What all authors do, they don't draw this thing separately. They draw this on the same axis. So I'm also drawing this on the same axis. But that doesn't mean that this A1, B1 object is in the presence of lens. This A1, B1 is in the absence of lens. When you remove the lens, this is your A1, B1 at a distance d. But when you put your lens, then this is the object AB, and your final image is at infinity. So this A1, B1 subtends some angle alpha. Is it clear? This AB and A1, B1.
Yes, sir.
This can be confusing. When you study books or you go through some notes, then this could be confusing. You will find two objects. You'll get confused from where these two objects came. AB is the object when you have the lens. A1, B1 is for the naked eye. So this beta by alpha is your angular magnification. Okay, in this triangle, next again, the same type of calculation, I need beta. So which triangle should I use, Nazia, for beta? Nazia, for beta angle, which triangle should I use?
Triangle FBO, sir.
FBO. What is F? No. F and B are
AO,
the same.
sir.
ABO, no?
No, ABO, sir.
BO or AFO, right? So what is tan beta here? Tan beta is AB by OB. AB by OB, or small angle approximation. So tan beta is equal to beta. For alpha, I'm using this triangle A1, B1, O. So your tan alpha will be A1, B1 by OB1. OB1. A1, B1 is object, so I can write A1, B1 as AB. So we can take the ratio, means instead of this beta, I'm substituting this. Instead of this alpha, I'm substituting this. When I take them, AB will cancel out, OB1 by OB. So what is OB1? That's minus D, OB minus U. See OB here? OB here, O to B here. This is nothing but the focal length. So you can say that your OB is minus F. So when you put these things here, minus D, minus F, minus cancel out, it's D by F. So magnification is D by F when your final image is at infinity. When your final image was at least distance, that your image magnification was 1 plus D by F. So in which case you get greater magnification? Noah, when your final image is at least distance or your final image is at infinity? Noah. Why? Arpit, in which case I get greater magnification when your final image is at least distance or your final image is at infinity? So at least distance of distinct mission, your magnification is 1 plus D by F. When your final image is at infinity, then magnification is just D by F. So obviously in d by f is less than 1 plus d by f. So when your final image is at infinity, your magnification is less now. But we still prefer this case. So when we use simple microscope, we try to prefer this case. The reason is when your final image is at infinity, then your eyes are relaxed as compared to your eye when your image is very close to eye. When your final image is at least distance, you put stress on your eye. It's not very comfortable to view this image. So we prefer the case when your final image is at infinity. So it's a conceptual question, like why, which case we prefer and why. We prefer the case for the simple microscope when your final image is infinity because it's comfortable to view this image. Then the image which is obtained at the least distance of distance. Please note it down. We'll do some numericals over it. I've shared the assignment of simple microscope, okay, on the group. So the assignment have questions from all instruments, but try to solve the questions from simple microscope at least. We'll do one question in class and then you can practice the rest later on. Can I scroll it?
No, 1 minute, sir.
So where is the image formed, sir?
Infinity. Parallel rays. So they will meet at infinity, you will get image at infinity.
Sir, when the image is at क्या
Image is at infinity and object at least distance. Can I scroll it now if you have drawn the ray diagram?
Yes, sir.
So when the image is at
Infinity. Written?
Yes, sir.
Yes,
It's
sir.
okay. So let's do this simple numerical. Please note this numerical. And please write your answer in the chat room. Huh?
Musashi is considered
सर ये जो राइट साइड में लिखा है ये लिखना
Yes, 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 yes. This is a conceptual question. See, although the magnification at infinity is less than the one when your final image is at least distance, but we still prefer the case when your final image is at infinity, because the eyes are more relaxed when you see an object which is an image which is at infinity. It's a conceptual question. And note down this numerical also. A simple formula based thing. No need to use sign convention in any formula of optical instrument. Just use these relations directly. Okay. Yes, no, it's correct. See the formula based thing. For final image at infinity, it's just d by f. When your final image is at least distance, it's 1 plus d by f. Then you can see. The rest I have shared the assignment. From that assignment, you can practice questions on simple microscope only. Don't try questions of compound microscope and telescope. That we will finish most probably the next class. So from my end, class is over. If you have doubts,